In a moment beyond imagining, the universe began. From a state where not even emptiness existed, came a cascade of space, time, energy, and matter. This beginning, the first breath of everything, marks a boundary not only in what we can observe, but in what we can even conceive. Because to ask what came before the universe is to ask a question that physics considers meaningless. There was no before, not in any way we understand. Time itself began when the universe began. This isn't just a poetic idea. It is one of the core implications of Einstein's theories, expanded upon by quantum cosmologists like Stephen Hawking. If space and time are interwoven, if space-time is one fabric, then the birth of the universe was also the birth of time. And if time itself had no prior moment, then there was no before for anything to exist within. Hawking famously likened it to asking what lies north of the North Pole. The question seems logical until you realize it dissolves under its own assumptions. At the North Pole, all directions are south. Beyond the universe's beginning, all timelines converge on nothing. And yet, here we are, living in a universe that is not only vast, but ancient. Based on measurements of cosmic microwave background radiation, an echo of the early universe still faintly glowing today, we estimate the age of the universe to be around 13.8 billion years. Some analyses, including provocative interpretations of galactic redshift data and star evolution models, have suggested a longer age, perhaps up to 26.7 billion years. But these remain speculative and unconfirmed. The mainstream consensus, supported by data from NASA's WMAP probe and the more recent precision of the European Space Agency's Planck mission, still points firmly to that 13.8 billion year mark. What was born in that first moment has grown into a structure of unimaginable scale. The observable universe, the portion we can see or be affected by, stretches across a sphere approximately 93 billion light-years in diameter. This figure may seem contradictory. If the universe is only 13.8 billion years old, how can we see something more than 6 times that far across? The answer lies not in faster-than-light travel, but in the fabric of space itself. While nothing can move through space faster than the speed of light, space itself can expand without limit, and it has. During the earliest epochs, space stretched so rapidly that distant regions were pushed beyond what light could reach, even as that light continues traveling toward us. It's important to remember that this 93 billion light-year diameter is not the size of the whole universe, only the observable patch available to us. There could be vastly more beyond, even infinitely more. But due to the finite speed of light and the finite age of the cosmos, we are forever bounded by a kind of cosmic horizon. Everything outside that horizon is not just out of reach. It is, in a real sense, out of existence from our point of view. We cannot see it, cannot touch it, and cannot ever be affected by it. From this perspective, we are like sailors on a vast ocean surrounded by a circular boundary beyond which the waters curve with the earth. Not because the ocean ends, but because the limits of vision do. The same is true for the cosmos, our instruments, our theories, our thoughts. Everything is constrained by this shimmering veil drawn by the speed of light and the passage of time. And what lies within that veil is not uniform. It is stitched with galaxies, stars, and planets, clumped and filamented like a sponge or a web. But at its foundation, at its first moment, the universe was something else, something hot, something dense, something simple. We believe the early cosmos was filled with a smooth, energetic plasma. No atoms, no stars, just raw energy and newly forming particles. This moment is what we refer to as the Big Bang. It is important to clarify what the Big Bang is and what it isn't. It is not an explosion in space. It is an expansion of space. Not a burst from one point outward into emptiness, but the sudden appearance of space itself, everywhere at once, unfolding and stretching with time. This expansion continues even now, though more slowly than in those first fiery instants. The Big Bang theory is not a complete origin story. Rather, it is the best model we have for how the universe evolved from a hot, dense state. It tells us how hydrogen formed, how helium emerged, how galaxies grew from tiny ripples in the early plasma. But it doesn't tell us why it all began, or what, if anything, set it in motion. In that sense, the Big Bang is not the spark, but the fire that followed. And so, we are left with a deeper question. Why does anything exist at all? Why is there something rather than nothing? This is not a question that science alone can answer, nor can it be resolved entirely by philosophy or mathematics. It lies at the edge of our understanding, where logic falters and mystery reigns. Still, the mystery is not empty. It is fertile. It invites exploration, not despair. In the earliest moment, beyond time, beyond matter, a single event gave rise to everything. A tapestry woven from nothing, its first thread a timeless spark. This is where the story begins. And yet, other visions of creation linger, whispering alternatives. Some see no singular start. Instead of a universe with a beginning, they imagine a cosmos without edges, without origin, without end. A reality that pulses, folds, or buds, endlessly remaking itself across scales we may never measure. These ideas do not dismiss the Big Bang. Rather, they reframe it. In place of an absolute beginning, they see a transition, a moment within a larger ongoing rhythm. One of the most compelling alternatives is the theory of the Big Bounce. In this vision, our expanding universe is just the latest act in a cosmic cycle, one preceded by contraction. Imagine the cosmos not as a one-way expansion from nothing, but as a heartbeat, a universe that grows, slows, contracts, and begins again. With each cycle, matter compresses, temperatures rise, and eventually, at the moment of highest density, a new expansion bursts forth, rebirthing space and time. This idea was explored in detail by physicist Paul Steinhardt, who helped develop models where the bounce is not just possible, but inevitable, given certain rules of physics. In these models, the Big Bang becomes not a beginning, but a bridge. Related to this is the conformal cyclic cosmology proposed by Roger Penrose, a Nobel laureate known for deep insights into relativity and black holes. Penrose's idea begins at the end, at the ultimate fate of our universe, when all matter decays, black holes evaporate, and only radiation remains. At that point, the universe is so stretched and so diffuse that, in a curious mathematical way, it resembles the ultra-compressed state of the Big Bang. Time loses its meaning at both ends of the scale, when things are infinitely dense and when they are infinitely spread. From that symmetry, Penrose suggests one cosmos could seed the next. Evidence? Perhaps. Penrose and colleagues have pointed to faint circular patterns in the cosmic microwave background, subtle echoes that, if confirmed, could hint at events before the Big Bang, but confirmation remains elusive. Other theorists step even further from our familiar notions of space and time. In the theory of eternal inflation, developed by Andrei Linde and supported by insights from Alexander Vilenkin, the rapid expansion of the early universe, known as cosmic inflation, never truly ends. Instead, it continues in distant regions, creating countless isolated pockets where inflation pauses and local universes take shape. Our universe would then be just one bubble in a vast cosmic foam. Each bubble could have its own laws of physics, its own constants, its own structure. Some might expand forever, others might collapse. Most would be utterly unlike ours. These are not mere guesses. They are grounded in the mathematics of inflation theory, which was originally devised to solve problems with the Big Bang model like the horizon and flatness puzzles. But eternal inflation extends the idea far beyond what we can observe. It is a natural consequence of the equations, though not one we can test directly. Yet, if the multiverse is real, it changes everything. It offers one answer to the question of fine-tuning, why the constants of nature seem so precisely set for life. In a multiverse, most universes would be sterile or unstable, but in rare bubbles like ours, the conditions just happen to be right for stars, for chemistry, for thought. And even that may not be the deepest layer. Enter the strange world of string theory, where the fundamental particles of nature are not point-like dots, but tiny vibrating loops, each mode of vibration giving rise to a different particle. In this framework, the universe exists not in 4 dimensions, 3 of space, 1 of time, but in 11. The extra dimensions are compactified, folded into shapes far too small to detect. But within this multidimensional stage, space itself can be a kind of membrane, a brain, floating in a higher dimensional bulk. Our universe may be one such brain. And the Big Bang? Perhaps it was a collision, a clash between brains that sparked a firestorm of energy and created the cosmos we inhabit. In the Randall-Sundrum model, for instance, gravity's weakness compared to other forces is explained by its ability to leak into extra dimensions. This opens the door to a whole new perspective on cosmology. Brains could drift, collide, recoil, generating new universes with each interaction. If these theories seem wild, they are, and yet they are not fantasies. They are built on serious mathematics, rooted in quantum mechanics and general relativity. They offer explanations, not just of the beginning, but of deep puzzles like particle mass, force unification, and cosmic structure. Still, no theory is without gaps. None of these alternatives has been directly observed. Some leave signatures so faint that they may never be testable. Others wait on technologies not yet invented or telescopes not yet launched. And yet, hints persist. The James Webb Space Telescope, launched to peer deeper into the past than ever before, has already found galaxies that appear unusually mature for their place in time. Structures that formed faster than standard models predicted. Some researchers have suggested that this might imply new physics, or even remnants of earlier cycles. But caution is warranted. These observations are not proof of a multiverse or of bounces or brains. They are puzzles, not yet mysteries. In the end, all these ideas, cyclic cosmologies, eternal inflations, multidimensional brains, seek to answer the same question. Is our universe a lone creation or part of something larger? Are we standing at the threshold of all reality or just one window among many? Perhaps we will never know. Perhaps the answer lies beyond our horizon, forever hidden. Or perhaps someday light or mathematics will reveal the deeper pattern. For now, we follow the threads. One theory leads to another, one question branches into more. Universes budding like leaves on an infinite tree. Regardless of prelude, the cosmos began its dance. Time, 5 seconds. Energy defines the universe's dawn. Before atoms, before stars, before space had meaning or time had direction, there was energy. Not the energy of engines or electricity, but something more primal, more condensed. It surged through the infant cosmos in forms we can barely imagine. In those first trillionths of a second, everything was heat. Not as warmth, but as motion. Raw, uncontrollable motion. Because temperature, at its essence, is motion, a measure of how fast particles move, how violently they jostle, how furiously they collide. The hotter the substance, the more kinetic its particles. And at the beginning of everything, the energy was so great that the very idea of particle was fluid. Matter and energy flowed together in a seething, shape-shifting field. To understand this, it helps to consider the limits. We know there is a lowest possible temperature, absolute zero, minus 273.15 degrees Celsius. At this point, all motion stops. Atoms cease vibrating. A perfect stillness, impossible to reach, but fundamental to thermodynamics. It is the baseline for everything else. But what of the other extreme? What is the hottest anything can possibly become? Here on Earth, in our most advanced laboratories, we've come close to recreating fragments of the early universe. In 2012, inside the Large Hadron Collider, a high-energy experiment smashed lead ions together at nearly the speed of light. For the briefest moment, the resulting collision created a temperature of 5.5 trillion degrees Celsius. That is 50 times hotter than the core of a supernova, a heat more intense than any naturally occurring process in the known cosmos. And yet, even this staggering figure is just a whisper next to what the universe achieved in its earliest instant. There is a theoretical maximum to temperature, a point beyond which heat cannot rise. Not because we lack imagination, but because the laws of physics break down. This limit is called the Planck temperature, and it sits at approximately 1.416808 times 10 to the 32nd Kelvin. That's a 1 followed by 32 zeros. It's the upper bound of thermodynamic possibility. Beyond this, the energy is so great that particles begin to collapse into micro black holes. Space-time itself begins to ripple, twist, and fragment. Quantum mechanics and general relativity, our two great pillars of understanding, begin to contradict each other, and the universe becomes unknowable. The Planck temperature is named after Max Planck, the German physicist who, in the early 20th century, helped give birth to quantum theory. By combining fundamental constants like the speed of light, gravitational strength, and Planck's own quantum constant, he derived natural units of time, length, and temperature. These define the smallest intervals possible in physics. The Planck time, for instance, is the shortest, meaningful tick of the cosmic clock, 5.39 times 10 to the negative 44 seconds. And the Planck length is the shortest measurable distance, 1.616 times 10 to the negative 35th meters. These numbers exist so far outside our daily experience that they may as well be fiction. A single atom is around 100 million times larger than the Planck length. The time it takes light to cross a proton is trillions of times longer than the Planck time. Human intuition fails at these extremes. We evolved to throw stones, not to measure infinities. Still, the numbers are real. They are built into the fabric of the universe, and during its first flickering instant, the universe reached the Planck temperature. All of it, the entire observable cosmos compressed into a space smaller than a single atom, its energy so dense, its temperature so fierce, that all known physics dissolves. We can't observe this moment directly. Our best particle colliders, even at the most extreme, operate around 10 to the power of 19 times weaker than the energy needed to probe the Planck regime. To access that scale, we would need a particle accelerator as large as the solar system, and even that might not be enough. And yet, through mathematics and theoretical models, we can glimpse its silhouette. We believe that just after the Planck era, less than a trillionth of a second after time began, the universe began to cool. It expanded rapidly, and with that expansion came a loss of density. Temperatures fell, forces began to differentiate, particles began to form. But for that first unmeasurable moment, the heat was absolute. Heat like an unyielding pulse, shaking reality's core. In that state, even the concepts of space and time are questionable. Energy was everywhere. Distances meant nothing. Duration had no meaning. There were no atoms, no light, no laws, only a superheated storm of probability and possibility. It is humbling to realize that we may never fully understand this phase. Our brains are not wired for it. Our instruments are not built for it. The physics of the Planck temperature is not merely unknown. It is unknowable within our current frameworks. It marks the limit of comprehension, the edge of the map. But we persist, because in understanding what lies just after this moment, we can glimpse the unfolding of the universe. We can trace the transformation from energy to matter, from chaos to form. And perhaps someday we will find a way to reach beyond even this wall of fire. For now, we look back as far as we can. We see a cosmos born in heat, a blaze that cooled into complexity. And in doing so, we understand just a little more about what it means to exist. At this pinnacle, scales shift to the infinitesimal. Beyond comprehension, reality compresses. From a cosmic blaze of unimaginable heat, the universe shrinks to a point so small, so dense, that our best tools for understanding begin to falter. This is not a world of stars or atoms or waves. It is a domain where even space and time dissolve into uncertainty. Welcome to the edge of what we can know. At this frontier, the universe exists at what physicists call the Planck scale, a realm defined by the constants of nature themselves. These aren't arbitrary numbers. They are the deepest fingerprints of the cosmos. In the early 1900s, German physicist Max Planck derived these scales while studying how light behaves when it interacts with matter. He noticed something strange. The energy of light seemed to come in discrete packets. This insight, revolutionary at the time, led him to define a new constant, now called the Planck constant, approximately 6.626 times 10 to the negative 34th joule seconds. It became the foundation of quantum theory. But Planck's work didn't stop there. By combining his constant with others, like the speed of light and the strength of gravity, he defined natural units of time, distance, temperature, and mass. These units are not based on human constructs like seconds or meters. They are woven into the structure of the universe. The Planck length, for instance, is about 1.616 times 10 to the negative 35th meters. That's so small, that if a proton were the size of the Earth, the Planck length would still be smaller than a speck of dust on its surface. The Planck time, meanwhile, is 5.39 times 10 to the negative 44 seconds. The time it takes for light to travel a single Planck length. These are not just small numbers. They represent thresholds beyond which current physics can no longer make reliable predictions. And during the universe's first moment, it occupied this scale. The observable universe, now more than 93 billion light-years across, was once compressed into a region no larger than a Planck length. All the matter, all the energy, all the potential for galaxies, stars, and life contained in something smaller than anything we can physically imagine. This raises an important distinction. The observable universe is not the whole universe. It is merely the part that light has had time to reach since the Big Bang. The full extent of the universe could be infinite, and if it is, it always was. The universe as a whole didn't shrink to a point, but our observable patch did. And at that moment, it became a boiling quantum field, a space where the rules of scale and structure break down. What does it mean for something to be that small? In our everyday world, we rely on clear boundaries. A chair is solid, a clock ticks, a ball bounces. But at the Planck scale, nothing is fixed. Particles blur into waves, positions become probabilities. Even space-time itself becomes uncertain. The smooth geometry that Einstein described, curving gently around stars and galaxies, begins to jitter, flicker, and ripple unpredictably. This is the heart of the challenge in modern physics. Our two great theories, general relativity and quantum mechanics, both work beautifully in their own domains. Relativity describes the very large. Quantum mechanics describes the very small. But at the Planck scale, where both theories must operate together, they clash. Gravity, under Einstein's framework, is smooth and continuous, a bending of space-time itself. Quantum mechanics, on the other hand, is discrete and probabilistic, filled with jumps and fluctuations. Try to apply both at the same time, and the equations explode into paradox. To resolve this, physicists are searching for a theory of quantum gravity, a single framework that unites the large and the small. Two main contenders have emerged. The first is string theory. In this model, all particles are actually tiny, vibrating strings. The differences between them, their mass, their charge, their force, depend on how these strings vibrate. But to make the math work, string theory requires extra dimensions, up to 11 in some versions. These extra dimensions are thought to be curled up so tightly that we don't notice them, but they shape the vibrations of strings and thus the nature of the particles. Importantly, string theory includes a particle called the graviton, a hypothetical messenger of gravity, much like photons carry light. The second contender is loop quantum gravity. Here, space-time itself is quantized. Instead of being continuous, it is made of tiny loops, discrete units of geometry, like atoms of space. These loops combine into a dynamic mesh, constantly shifting and rearranging. In this model, the smooth curves of relativity are an illusion, just the large-scale behavior of countless quantum loops. Both theories remain incomplete, both are mathematically rich, and both strive to answer the same question: what happened at the edge of reality? At the Planck scale, the universe was not simply small, it was undefined. Distances fluctuated. Time itself was jittery. Cause and effect blurred. There was no meaningful before because even temporal ordering was unreliable. And yet, within that chaos, something happened. A structure began to emerge, a balance of energy and fields. Laws began to crystallize, even if just temporarily. What was purely chaotic became, for a moment, something almost stable. We can think of this moment as a kind of cosmic overture. All the themes that will define the universe, mass, gravity, particles, forces, exist here in their rawest form. They have not yet split, not yet differentiated, but they are present as potential, compressed, waiting, a pinpoint holding the cosmos like a single note containing a symphony. This is not a time we can observe directly. There is no telescope, no instrument that can peer into this scale. It lies beyond the reach of light, beyond the stretch of matter, and yet, through theory and inference, we build an image of it, not because we must, but because it is there, beckoning from the first moment. The Planck scale is not just a frontier of physics. It is a boundary of thought, a limit beyond which imagination itself must stretch. In this Planck era, chaos takes form. Here, the cosmos experiments with itself. In this first instant, just 10 to the negative 43rd seconds after the beginning, there are no galaxies, no atoms, no laws that resemble anything we've ever known. This is the Planck era, the briefest sliver of time in which the universe, still smaller than a proton, boils with energy and uncertainty. It is a moment so fleeting, so compressed, that even the idea of a moment may not apply. What defines this era is not structure, but potential, not motion, but fluctuation. It is a phase governed by the deepest conflict in modern physics, a standoff between Einstein's relativity, which explains the fabric of space and time, and quantum mechanics, which governs the unpredictable dance of particles and fields. At larger scales, these two frameworks are masterpieces. General relativity predicts black holes, gravitational waves, and the curvature of space-time itself with astonishing precision. Quantum theory, meanwhile, underpins the entire world of particles, chemistry, and electronics. But at the Planck scale, where all distances are smaller than 1.616 times 10 to the negative 35th meters, and where time intervals are shorter than 5.39 times 10 to the negative 44th seconds, these two pillars of science become incompatible. Relativity demands smoothness. Quantum theory insists on jitter. And the result is chaos. In this chaos, space-time does not stretch like a calm sheet. It bubbles. Physicist John Wheeler coined the term quantum foam to describe this state. At this scale, space-time is not continuous. It froths and churns, flickering unpredictably like the surface of a boiling liquid. Little pockets appear and vanish, virtual black holes, tunnels, tiny wormholes that wink into existence and collapse in fractions of a second. These are not science fiction. They are mathematical possibilities within quantum gravity models. Imagine a seething broth where the rules are fluid, where dimensions twist and fold, where causality is optional. Every point in space is not a dot but a haze of probabilities. Every tick of time is a guess. In this foaming matrix, nothing holds still, nothing lasts, yet everything we know is waiting to emerge. The density of the universe at this time is mind-bending, estimated at around 10 to the power of 93 grams per cubic centimeter. For comparison, a neutron star, one of the densest known objects, packs about 10 to the 14th grams per cubic centimeter. That's nearly 80 orders of magnitude less dense than the universe during the Planck era. If a neutron star is crushing, this is absolute, And yet, despite that staggering density, the universe is not static. It is dynamic, expanding, stretching, and cooling. Even as space-time foams and flickers, it grows rapidly. This expansion does not erase the quantum chaos, it merely dilutes it, softens it, prepares the ground for what will come next. One might ask, if gravity is so important at these scales, why can't we simply apply our current theories to understand it? The answer lies in the nature of gravity itself. In Einstein's theory, gravity is not a force in the traditional sense. It is a warping of space-time caused by mass and energy. But in quantum theory, all forces arise from the exchange of particles, photons for electromagnetism, gluons for the strong force. To unify gravity with quantum mechanics, we would need a quantum particle of gravity, a graviton, and a field theory to support it. Yet no such graviton has been observed, and attempts to quantize gravity using traditional methods lead to infinite energies and nonsensical results. This is why physicists seek alternatives like string theory, where the graviton emerges naturally from the vibrations of tiny strings, or loop quantum gravity, where space-time itself is made of discrete loops that combine into larger structures. These models attempt to describe what the universe was doing during the Planck era, not just mathematically, but physically. What happens to a particle when it is smaller than the space it occupies? What happens to space when it is made of quantum elements? We don't yet know. The equations grow complex, the predictions become probabilistic, and experiments, for now, are beyond reach. This phase is not empty of meaning. It is a threshold, a bridge between the unknowable and the unfolding. From this foam, the rules of our universe will be born, not given, but selected, emerging from the chaotic stew like ripples from a storm, a bubbling froth where space and time blur. This image is not just metaphor. It reflects our best attempts to describe a realm where the fabric of existence is not yet woven, where logic may falter, but curiosity persists. Some theorists propose that even the constants of nature, values like the speed of light, the strength of gravity, the mass of particles, could have been shaped or influenced during this frothing phase, not chosen by design, but frozen by chance as the quantum foam settled into a more ordered state. If this is true, then our entire universe is a kind of fossil, a cooled relic of a much stranger moment. We often imagine beginnings as clean, a switch flipped, a curtain raised. But the beginning of the universe was not like that. It was messy, jittery, alive with possibilities. The Planck era is not a moment we can freeze in time. It is a boundary, a phase change, a moment when the cosmos had not yet chosen its laws. Reality's rules were unwritten, and yet they were coming. Because from this froth, patterns emerge. As the foam begins to smooth, energy begins to channel, forces begin to form. The wild quantum fluctuations start to average out, and as the universe expands, the scales shift. The chaotic becomes structured, the undefined becomes precise. It is here, in this transition, that gravity takes its classical form. That space-time, once uncertain, begins to stretch with purpose. And with that, the stage is set for the next great chapter of cosmic evolution. As the heat ebbs, forces begin to unify. Our world rests on 4 pillars, not of stone or myth, but of interaction. Every motion, every transformation, every event, from the spin of a galaxy to the flicker of a neuron, is governed by just 4 fundamental forces. These forces are the silent architects of reality. They hold atoms together. They ignite stars. They guide the fall of an apple and a fusion of hydrogen. They are strong, weak, electromagnetic, and gravitational. At the surface, these forces seem distinct, different in strength, in range, in purpose. But deep in the early universe, under temperatures no longer found in nature, they may have been one. We begin with the strong force, the mightiest of all. It binds protons and neutrons inside the atomic nucleus, overcoming the fierce repulsion between their positive charges. It does this through particles called gluons, which carry a kind of color charge, not unlike electric charge, but operating under different rules. Unlike gravity or magnetism, the strong force grows stronger with distance, snapping particles back together like an elastic band stretched too far. It is what makes matter stable. Without it, every atom would disintegrate. Next is the weak force, subtle but essential. It governs radioactive decay, allowing particles to transform. Through carriers known as W and Z bosons, it enables a neutron to become a proton or vice versa, releasing neutrinos and energy in the process. This transformation plays a quiet but crucial role in nuclear reactions, especially in the fusion processes inside stars, including our Sun. Without the weak force, the Sun could not shine. Then comes electromagnetism, perhaps the most familiar force. It acts through photons, the quanta of light, and affects anything with electric charge. This is the force behind lightning and magnetism, but also behind chemistry, electronics, and life itself. It powers the signals in your brain, the glow of your screen, the wave from your remote control. It is long-ranged, infinite in reach, and vastly stronger than gravity on human scales. And finally, gravity, the weakest of all, yet the most commanding across vast distances. It shapes planets, orbits, and the expansion of the cosmos. But it is 10 trillion times weaker than the strong force, about 10 to the negative 38th power by comparison. It has no known repulsive counterpart and is believed to act through a hypothetical particle, the graviton, still unobserved. These are the four forces. In our everyday world, they appear distinct, their effects separated by scale and function. But under the furnace conditions of the early universe, temperatures approaching 10 to the power of 28 Kelvin, the differences begin to melt away. At such energies, the forces lose their identities. Their carriers become indistinguishable. Their effects converge. It is as if four rivers, each with its own course and color, flow into a single sea, a unified force field from which all later interactions emerge. Physicists call this the era of force unification. It likely occurred within the first 10 to the negative 36 seconds after the Big Bang. The first stage of this unification brings together the electromagnetic and weak forces into the electro-weak force, a merger confirmed in particle accelerators like CERN. At high energies, the photon W and Z bosons are nearly the same particle. Only as the universe cooled did their differences harden into form. Beyond that, theoretical models suggest that the strong force also joins in, leading to a grand unified theory, or GUT. In such models, all three forces, strong, weak, and electromagnetic, were once a single interaction, described by elegant mathematical symmetry. These theories predict exotic phenomena such as proton decay, that we've not yet observed but which remain active areas of research. Further still, physicists dream of a theory of everything, one that includes gravity as well. But here, progress slows. Gravity's extreme weakness and unique nature make it hard to fit into the quantum puzzle. String theory offers one path, proposing that all particles are just different vibrations of tiny loops. Loop quantum gravity offers another, quantizing space itself. Both aim to find the unifying thread. Still, even without a final answer, the implications are profound. If the forces we see now were once unified, then the universe itself has changed in kind, not just in shape. The forces split apart as the universe cooled, like a hot metal alloy separating into distinct layers. This symmetry breaking wasn't just structural. It defined how particles interact, how matter forms, how stars ignite, and how time unfolds. The symmetry was not lost. It was hidden, buried beneath layers of cooling, masked by the expansion of space. In moments of extreme heat, like in particle collisions or the hearts of newborn stars, tiny echoes of unity still flicker into being. Forces like rivers converging in the heat. It's easy to forget, surrounded by the quiet order of our lives, that these forces are always at work. Every breath, every beam of sunlight, every neural signal is a conversation among them. What we call reality is the echo of their interaction, the result of their long divergence from a common beginning. And this, too, reflects a deeper truth. That complexity can arise from unity. That what seems separate may be joined. That the universe, at its most extreme, reveals a kind of elegant simplicity. In the end, the story of the forces is not just a tale of particles and fields. It is a story of differentiation, of identity, of evolution. The cosmos did not start with diversity. It began with singularity, with unification, with symmetry. Everything else followed. In the furnace, they blur into one. At energies unfathomable, the universe became a stage for a wild, primal symphony, a brief but dazzling era, when order and identity were still fluid. From 10 to the negative 36th to 10 to the negative 32nd seconds after the Big Bang, the cosmos entered the grand unification epoch, a moment when three of the four fundamental forces, the strong, weak, and electromagnetic, merged into one unified interaction. Gravity remained separate, aloof in its own enigmatic domain, but everything else joined together in a state of shimmering simplicity. And yet, simplicity can be deceiving. Beneath that unified field, chaos reigned. Particles as we know them, quarks, leptons, bosons, had not yet solidified their identities. They were born from the high-energy interactions of that field, popping in and out of existence as quantum probabilities. Matter and antimatter were forming in equal measure, like dancers partnered in perfect symmetry, only to vanish in mutual annihilation. Everything was in motion, everything uncertain. Imagine a spinning coin caught in midair. Heads and tails are not yet defined, only a blur of motion, a possibility. This is the coin of particle identity in the grand unification epoch. Nothing was settled. Everything was oscillating. In this regime, quarks and leptons may not have been distinct categories. Instead, they flowed from the same source, interchangeable under the right conditions, indistinguishable in the haze of energy. Photons, the carriers of light, were just one face among many. The forces themselves had not yet separated. All interactions came from a single electro-strong field, mediated by theoretical particles known as X and Y bosons. These bosons, if they exist, would be heavier than anything we've ever detected, requiring energies on the order of 10 to the power of 16 giga-electron volts, 1 trillion times more than what the Large Hadron Collider can currently achieve. They would have carried the unified force, acting equally on particles of all kinds. But like the coin slowing in its spin, this indistinction could not last. As the universe expanded and cooled, still blisteringly hot, but no longer infinite, these exotic bosons faded. The forces they once merged began to split. It was during this transition, this breaking of symmetry, that something subtle but profound may have occurred. The beginning of baryon asymmetry, the imbalance between matter and antimatter. Under perfect symmetry, every particle has a counterpart. An electron has a positron, a proton has an antiproton. In theory, when matter and antimatter meet, they annihilate into pure energy. If the early universe had been truly symmetrical, it should have left behind nothing but light. No stars, no planets, no observers. And yet, here we are. Somewhere, somehow, matter gained a slight edge. For every billion particle-antiparticle pairs, one extra particle of matter remained. That lonely surplus, just 1 in a billion, is what makes up everything we see. Every rock, every cell, every galaxy is the residue of this imbalance. The grand unification epoch may hold the key to this mystery. During the decay of X and Y bosons, or through interactions involving high-energy transitions, the laws of physics may have briefly allowed CP violation, a subtle asymmetry in how matter and antimatter behave. It would not have been dramatic. It would not have been obvious. But even the slightest skew, repeated across cosmic scales, could tip the balance. Thus, what appears as a chaotic storm of energy may have been the crucible for the structure of reality. A phase where randomness gave rise to bias, where fluctuation produced form. A dance where identities shift until the coin slows. This phase, though hidden from observation, continues to shape our universe. It influences the abundance of particles, the dominance of matter, the composition of the cosmos. And though we may never directly observe X or Y bosons, their ghostly fingerprints may linger in patterns of cosmic background radiation, in the ratios of particles, in the asymmetry of what endures. Particle physicists have spent decades building grand unified theories, mathematical frameworks that combine the standard model's forces into a single elegant equation. These theories often predict new symmetries, new particles, new interactions. Some involve supersymmetry, where each particle has a heavier twin. Others involve additional dimensions, compactified and hidden. All seek the same goal: to explain how the early universe transitioned from unity to diversity, from formless energy to structured interaction. But despite the beauty, these theories remain speculative. They have not yet been confirmed by experiment. The energies required are immense beyond current reach. The timescales are too short, the events too ancient. And so we are left with clues, not answers. Still, the physics is compelling. The mathematics is consistent. And the narrative, the evolution from uniformity to complexity, is echoed across nature. Ice, crystals forming from water, galaxies from gas, identity emerging from chaos. We often think of creation as a moment of clarity, but in truth, creation may be a moment of confusion, a symphony without a conductor, finding order through discord. The grand unification epoch was not quiet. It was not gentle. It was a storm, a burst of indistinction that ended in choice. The forces broke apart. The particles settled. The coin, once spinning, began to fall. But flaws in this picture demand a solution. Theories fit particles, but the cosmos resists. For all its power, the Big Bang model, our best description of how the universe evolved, runs into paradox when scaled up. It explains how matter formed, how light scattered, how galaxies emerged. But when we step back and gaze across billions of light years, something strange appears. The universe, vast and ancient, looks too tidy, too balanced, too smooth. It's as if we found a 1,000-piece puzzle, already assembled without ever having opened the box. This is the horizon problem. When we look in opposite directions across the sky, we see regions of space separated by more than 90 billion light years. The light from these regions has only just reached us, yet the cosmic microwave background, the afterglow of the early universe, shines at nearly the exact same temperature in all directions, about 2.725 Kelvin. It's a uniformity so precise that the variation is just 1 part in 100,000. But how could these distant regions be identical if no signal has ever passed between them? According to the standard Big Bang model, they've never had time to interact, to exchange heat, to equilibrate. They should be different, and yet they are not. Then comes the flatness problem. Einstein's equations allow for 3 possible curvatures of space: positive, like a sphere; negative, like a saddle; or perfectly flat. The fate of the universe depends on this curvature, whether it will collapse, drift forever, or hover in balance. But for the universe to be as flat as we observe today, it must have started with an astonishing level of precision, like placing a coin on its edge and watching it remain upright for billions of years. There's also the monopole problem. Certain particle physics theories predict the creation of magnetic monopoles, single magnetic poles with no counterpart. These should have been produced in abundance during the early universe. Yet none have been found, not one. All of this paints a strange picture, a cosmos that seems, at its larger scales, almost too perfect. Not in its beauty, but in its balance. A cosmos too perfect, like a puzzle with no edges. Enter Alan Guth, a young physicist working on particle interactions in the late 1970s. While exploring the dynamics of grand unified theories, he encountered an idea, simple in concept, profound in consequence. What if, in the universe's first moments, space didn't just expand, but expanded exponentially? This idea became the theory of cosmic inflation. According to Guth's model, a fraction of a second after the Big Bang, around 10 to the negative 36 power seconds, the universe underwent a burst of expansion so rapid it outpaced even the speed of light. Not because anything moved faster than light, but because space itself expanded faster than light could traverse it. In less than 10 to the negative 32nd seconds, the universe grew from smaller than a proton to the size of a grapefruit, or larger. This sudden stretching smoothed out all irregularities, flattened curvature, and expanded any primordial region of thermal equilibrium far beyond our current horizon. Inflation, in one stroke, solves the horizon problem. If all regions of space were once close enough to interact before inflation stretched them apart, then their uniformity makes sense. It solves the flatness problem because exponential expansion would drive any curvature toward flatness, just as blowing up a balloon flattens a tiny patch. And it solves the monopole problem because any exotic relics would be diluted to near invisibility in the rapid swelling of space. Inflation also provides a mechanism for seeding structure. tiny quantum fluctuations, random blips in the inflationary field, were stretched to cosmic scales. These became the slight density variations that billions of years later would collapse into galaxies, stars, and planets. These predictions aren't just elegant, they're testable. The cosmic microwave background, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, contains subtle patterns of temperature variation, just as inflation predicts. These variations match the statistical distribution expected from quantum fluctuations amplified by inflation. Still, inflation is not the final word. It raises questions of its own. What caused inflation to start? What made it stop? Is it still happening elsewhere in a multiverse of ever-growing regions? Observations from the James Webb Space Telescope have added nuance. Some of the earliest galaxies appear more mature than models anticipated. This does not disprove inflation or the Big Bang. It suggests we may need to refine our understanding of how structure forms within the expanding universe. Stars may form faster, dust may clump sooner, but the large-scale predictions of inflation remain consistent with what we observe. Inflation transforms our view of the universe, not just in scale, but in logic. It reminds us that the early universe wasn't merely a burst of matter and heat, but a stage of transition, a moment where the laws of physics were reshaped by geometry itself. A sudden expansion resolves the riddle. A fleeting burst reshapes reality. In the tiniest sliver of time, less than 10 to the negative 32nd power seconds, early universe took a leap so vast, it transformed the structure of everything to come. This event, called cosmic inflation, was not a gentle swelling, but a runaway expansion. It didn't unfold gradually. It exploded outward faster than light, not by breaking the rules of motion, but by stretching the very fabric of space itself. The idea, first proposed by Alan Guth in 1979, began as a patch to fix problems in the standard Big Bang model. But it became something deeper, a doorway into a new understanding of the universe's origins. Before inflation, the early universe may have resembled a chaotic energy-filled patch, a microscopic zone of false vacuum energy. Within this patch, all the forces of nature were still unified. But something triggered a shift. A phase transition occurred. And as this false vacuum decayed, it released energy into expansion. Space didn't just grow, it doubled in size again and again, around 90 times in total. Each doubling took less than 10 to the negative 35th seconds, but the effects were monumental. The result? A universe that grew by a factor of at least 10 to the 26th power, or about an octillion-fold increase in volume. A region once smaller than a proton became large enough to contain the entire observable universe and more. What we see today, billions of galaxies scattered across 93 billion light-years, is just a tiny fraction of the bubble inflated in that early flash. This expansion stretched space flat, like a sheet pulled tight. It made what may have been curved or wrinkled appear smooth to any observer within. Much like standing on the surface of a vast ocean, the curvature vanishes across your horizon. This explains why the universe appears so geometrically flat, not because it always was, but because inflation erased the irregularities. It also resolved the horizon problem. Before inflation, every part of the universe was close enough to interact, to exchange light and energy, to settle into thermal equilibrium. When inflation occurred, it took that uniformity and spread it far and wide, beyond the reach of light today. The smooth temperature of the cosmic microwave background, the match between regions too distant to have communicated, now makes sense. They once shared a common past, and inflation pulled them apart. As for magnetic monopoles and other predicted relics of high-energy physics, they were not erased, but diluted. Imagine sprinkling a pinch of dust into a balloon, then inflating it to the size of a planet. The dust doesn't vanish, but its density becomes negligible. So too with the monopoles. Inflation took whatever was there and stretched it beyond detection. And from this expansion came something unexpected: the seeds of cosmic structure. At the quantum level, the inflationary field was not smooth. It fluctuated, tiny, random jitters in energy density. Normally, such fluctuations are confined to the smallest scales. But during inflation, they were stretched to astronomical proportions. Regions slightly denser than others became gravitational wells, attracting matter as the universe cooled. These became the scaffolding for galaxies, clusters, and cosmic filaments. What began as quantum randomness became the visible shape of the universe. This link between quantum mechanics and cosmic architecture is one of inflation's most astonishing insights. The ripples we see in the cosmic microwave background, mapped with precision by satellites like Planck, match the statistical fingerprints of these quantum fluctuations. A theory built to fix problems turned out to predict structure itself. Visualize it this way: a speck of space governed by quantum uncertainty inflates like a balloon. The folds and creases of that balloon, once subatomic, now span millions of light years, paper folded from a speck to a supercluster. Inflation is not without questions. We still seek a full understanding of the inflaton field, the hypothetical energy source behind the expansion. We don't know whether inflation was a one-time event or an ongoing process, with other regions of space inflating eternally beyond our horizon. Some models suggest a multiverse, a collection of inflated bubbles, each with its own laws and constants. But these ideas, while intriguing, remain beyond direct observation. What we do know is that inflation provides a compelling solution to the Big Bang's flaws. It explains why the universe looks the way it does, not chaotic, but ordered, not curved, but flat, not patchy, but uniform. And it ties together the smallest scales of reality with the largest. Inflation is not merely a flash of growth. It is the moment when structure began, when randomness became form, when the stage was set for atoms, light, stars, and life. With space expanded, matter takes the stage. Balance yields to diversity. As the universe cooled from its inflationary surge, it entered a new chapter, one of separation, of identity, of structure. Around 10 to the power of minus 12 seconds after the beginning, a delicate transformation took place. What had been a single unified force, electroweak, fractured into two distinct interactions. The electromagnetic force, which shapes light and chemistry, and the weak nuclear force responsible for radioactive decay. This moment, though invisible to the eye, defines the texture of reality. At higher temperatures, the distinction between these forces vanishes. They are two faces of a single interaction, but as the universe cooled, the symmetry broke. Like water freezing into ice, the change wasn't violent, but it rewrote the rules. A uniform phase yielded to structure. Possibility gave way to form. And at the center of this transformation lies the Higgs field. Unlike gravity or magnetism, the Higgs field doesn't push or pull, it permeates. It exists everywhere, constantly. It does not flicker or surge. It rests, unchanging, like a quiet pressure against the vacuum. But when certain particles move through it, they encounter resistance, not friction, but interaction. And this interaction is what gives them mass. Before this moment, particles were massless. They moved at the speed of light. Photons still do. They pass through the Higgs field without effect. But other particles, like the W and Z bosons, encounter the field and slow down. This slowing is not mechanical. It is intrinsic, a reflection of how strongly each particle couples with the field. The W boson, for instance, becomes about 80 times heavier than a proton. The Z boson even more. And the Higgs boson itself, the quantum ripple of the field, has a mass of 125 giga-electronvolts, as confirmed by the Large Hadron Collider in 2012 discovery, was not a surprise, but it was a triumph. A final, crucial piece of the Standard Model puzzle made real. This moment of electroweak symmetry breaking is not just a physical event. It is a shift in the character of reality. From a unified field, nature selects a new arrangement, one in which the photon becomes massless and free, while the W and Z become heavy, restricted. Their roles diverge, their powers specialize. Imagine a room full of people standing still. A new guest enters, and as they move through the crowd, others gather around them. The more people who gather, the harder it is for them to move. This metaphor, sometimes called the cocktail party model, helps visualize how interaction with the Higgs field produces inertia, not resistance in the usual sense, but mass, the reluctance of a particle to accelerate. A field ripples, weighing the weightless. Not all particles are affected equally. The electron acquires a small mass. The top quark, by contrast, becomes the heaviest known elementary particle. Why the Higgs field couples more strongly to some particles than others remains a mystery. We know how it works, but not fully why. Why do masses vary so dramatically? What fixes the strength of these couplings? These are not rhetorical questions. They are open frontiers. Still, the effect is undeniable. With mass comes distinction. Particles now differ not just in charge or spin, but in inertia, in how they bend under force, in how they assemble into larger forms. Without the Higgs field, the universe would be unrecognizable. Atoms would not exist. Forces would act, but nothing would bind. Light would shine, but there would be no matter to reflect it. In a sense, the Higgs mechanism grounds reality, turning a sea of possibilities into a landscape of form. And just as inflation gave rise to space and quantum ripples seeded structure, this symmetry breaking gave rise to substance. Not yet the atoms of chemistry, but the building blocks from which they would be made. Particles with mass can now cluster, decay, and interact in new ways. The primordial soup grows more complex. It is in these moments, just fractions of a second old, that the universe begins to choose its cast. Forces are divided, roles are defined. The energy of the early cosmos does not vanish. It condenses, transforms, and takes on form. The universe is still expanding, still cooling, but now it is also sorting. The Higgs boson, elusive and ephemeral, decays quickly, but its field remains, a constant backdrop to all motion, all form, a hidden actor in every physical event. We may never know the full reason why this field exists or why it takes the shape it does. But in understanding its role, we grasp something fundamental about why things are the way they are, why light travels free while matter resists, why some particles decay while others endure. With mass born, particles swirl into chaos. Particles find identity, but not yet structure. In the moments following the electroweak split, the universe remains a storm of energy and motion. Temperatures hover near 10 to the 12th Kelvin, and matter, as we know it, does not yet exist. Instead, the cosmos is filled with an exotic fluid, a quark-gluon plasma, where particles collide, emerge, vanish, and reappear in endless combinations. This is the quark era, a span lasting from around 10 to the minus 12th seconds to 10 to the minus 6th seconds after the Big Bang. In this fiery state, quarks and gluons roam free, untethered by the forces that will later bind them. The plasma is dense, chaotic, and uniform. It is also temporary. Quarks are the fundamental constituents of matter. There are 6 types: up, down, charm, strange, top, and bottom. But in this early phase, only the lightest matter-forming kinds dominate: up and down quarks. Alongside them drift leptons like electrons and neutrinos, and the force-carrying bosons from earlier phases: photons, W and Z particles, and gluons. These are the ingredients of the Standard Model, the framework that describes all known particles and interactions, apart from gravity. At this point, matter still swims freely in the primordial sea. Quarks have not yet combined into protons or neutrons. Electrons are too energetic to be caught by any nucleus. The universe is hot enough to keep everything dissociated, like a soup too hot to congeal. And yet, amid this energy, the structure begins to form, not in bonds, but in balance. Something subtle persists through this chaos, a tiny asymmetry between matter and antimatter. Quarks and antiquarks, leptons and antileptons, created in near equal pairs, continue to annihilate. But for every billion such pairs, one extra particle of matter remains. It's a razor-thin imbalance, but it will shape the entire visible universe. As the plasma cools and the collisions lessen, matter wins. Barely. The leftovers become everything. By about 1/1,000,000th of a second after the Big Bang, the universe begins to change again. Temperatures fall just enough for the strong nuclear force carried by gluons to begin confining quarks. 3 at a time, they bind into hadrons. The most stable of these are protons and neutrons, the future building blocks of atomic nuclei. This transition is sometimes called the quark-hadron transition or the hadron epoch. From free particles to composite ones, the universe shifts from pure plasma to potential substance. But these protons are not simply bags of quarks. Their mass tells a deeper story. A proton contains 2 up quarks and 1 down quark, each with a tiny mass. But if you add up their individual masses, you get only about 9% of the total proton mass. The remaining 91% comes from energy, from the gluon field that binds them, from the buzzing activity inside the proton itself. This is Einstein's equation in action: E equals mc squared. Mass is not only from substance, but from motion, from energy, from confinement. A cosmic soup, simmering with potential. This image captures the character of the quark era. Nothing yet is solid. Everything is flux. Yet from this flux comes form, from chaos, composition. Meanwhile, electrons, still moving freely, wait for their moment. They are not part of protons or neutrons, but they will be. Soon, as the universe cools further, they will bind into atoms. But not yet. For now, the universe remains a plasma, a hot, dense fog of charged particles. Light cannot travel freely. Photons scatter off electrons in all directions. The cosmos glows, but not clearly. It is brilliant, but opaque. This is the final moment before matter as we know it takes hold. From the quark-gluon plasma, the stable building blocks have emerged. The universe is still expanding, still cooling, but the ingredients of stars and life are now in place. It's remarkable that all of this, the identity of particles, the formation of protons, the survival of matter over antimatter, was determined in the first second of existence. Every galaxy, every planet, every element of our bodies traces back to this plasma, to this state of unformed energy folding into form. What emerges from this moment is not yet structure, but possibility. The stable particles that will combine into atoms, molecules, and stars. Constants shape what follows. Constants dictate creation's recipe, with quarks locked into protons and neutrons and the universe now past its first second. The cosmic conditions finally allow something more delicate: fusion. This is the era of primordial nucleosynthesis, a narrow window from 1 second to about 20 minutes after the Big Bang, when the universe becomes a forge. The temperature is still extreme, around 1 billion Kelvin, but cooling steadily. In this thermal decline, the first nuclei can form, not atoms yet, but the atomic cores that will one day anchor every element. It begins with a subtle dance between protons and neutrons. These are the lightest baryons, and they interact under the influence of the weak nuclear force, which can convert one into the other. In the earliest instance, this conversion happens rapidly, but as the universe expands, the rate slows. Around 1 second, this interchange effectively freezes. Neutrons, slightly heavier and less stable, begin to decay, unless they find a partner quickly. Roughly 1 neutron for every 7 protons survives into the nucleosynthesis era. This ratio sets the elemental outcome. The most likely union is between 2 protons and 2 neutrons, forming helium-4, the most stable light nucleus. Others, deuterium, helium-3, and traces of lithium-7, form as well, but only in small amounts. The universe at this point is like a vast furnace cooling through a precise temperature curve. If it cooled too slowly, all matter might fuse into helium. If too quickly, even helium wouldn't form. But conditions are balanced, just right. Long enough for about 25% of the universe's mass to become helium, with the rest remaining mostly hydrogen. This ratio, 3 parts hydrogen to 1 part helium by mass, or about 12:1 by particle count, was first predicted by Ralph Alpha and George Gamow in the mid-20th century, long before it was observed. Their calculation, built on fundamental physics, became a cornerstone of Big Bang cosmology. And yet, this process is far from simple. Fusion must first overcome a major hurdle: the deuterium bottleneck. Free neutrons and protons must bind into deuterium, a proton-neutron nucleus. But at high temperatures, photons break these fragile unions apart as fast as they form. Only when the universe cools below a critical point can deuterium accumulate, opening the path to helium and other light elements. This bottleneck delays fusion for crucial seconds, setting the stage for the element distribution we see today. A furnace sparks, crafting the first elements. This fusion is not like what happens in stars. It's a one-time, universe-wide process. The energy comes not from gravitational collapse, but from the momentum of creation itself, and it leaves a permanent signature: the cosmic abundance of elements. No heavier elements form in this epoch. the temperature falls too quickly. Carbon, oxygen, and iron must wait for stellar interiors billions of years later. But the light elements forged here, hydrogen, helium, deuterium, lithium, are still with us, untouched, unchanged. Every glass of water contains hydrogen born in the first 3 minutes. And just as matter begins to settle into nuclei, another background decouples. The neutrino background. These ghostly particles, barely interactive, streamed freely from about 1 second onward. Though undetectable with current instruments, they fill space even now, echoing the early universe in their own silent way. What makes this period so remarkable is its precision. The strengths of the nuclear forces, the masses of the particles, the rate of expansion, all must align for fusion to produce a chemical foundation that allows for complexity. A slightly different universe might have converted everything to helium. Without hydrogen, there would be no water, no stars like our sun, no biochemistry, no life. From plasma to particles, from chaos to nuclei, the universe has taken another step toward form. What remains is still a dense, hot fog. Atoms do not yet exist. Electrons remain free. Light cannot yet travel far without scattering. The cosmos glows, but the glow is trapped, caught in the plasma of charged particles. And so, while elements now exist, the light that might reveal them is still delayed. Elements form, yet light remains trapped. Electrons settle and clarity emerges. After hundreds of thousands of years, the universe, once an opaque sea of charged particles, undergoes a quiet revolution. The temperature has dropped to around 3000 Kelvin, cool enough for protons and electrons to come together at last, forming the first neutral atoms. This moment, occurring about 380,000 years after the Big Bang, marks the era of recombination. Until now, light could not travel far. Photons, those carriers of electromagnetic energy, were constantly scattered by free electrons in a dense plasma. The universe glowed, but the glow was trapped, bouncing endlessly in a fog of interaction. But with the formation of atoms, that fog begins to clear. The electrons are no longer free. The photons, once imprisoned, find open space. They travel. And that journey has never stopped. This is the birth of the cosmic microwave background, a relic light that still fills the universe today. Recombination is not a violent act. It's a process of settling, of bonding. As atoms form, mostly hydrogen with some helium and trace lithium, the universe becomes transparent for the first time. Light breaks free from its prison and begins its long journey across space and time. What escapes in that moment is not a single flash, but a sea of photons moving in all directions. These photons were born in a universe glowing orange-white, with a black body temperature of about 3000 Kelvin. But the universe has expanded since then. Space itself has stretched, and with it, the wavelengths of these ancient photons. They've been redshifted down into the microwave range, cooling to a temperature of just 2.725 Kelvin today. And yet, they remain. We detect them in every direction. The CMB, as it is known, is the most ancient light we can see. Not from stars or galaxies, but from a time before either existed. It carries within it the imprints of everything that came before. The density fluctuations from inflation, the composition of the early universe, the scale of primordial sound waves. It is, in many ways, a photograph of the universe's childhood. Within this light, subtle patterns appear: baryon acoustic oscillations, frozen ripples in the plasma from before recombination. These are like sound waves in the early universe, oscillating through the hot, dense fluid of photons and baryons. When recombination occurs, these waves freeze into the structure of matter. Billions of years later, their echoes are still visible in the large-scale distribution of galaxies. The universe remembers. What makes this period so profound is its subtlety. To our eyes, nothing dramatic happens. There are no explosions, no new particles, no changes in the elemental makeup. And yet, everything changes. The cosmos goes from opaque to transparent, from hidden to seen, from confusion to clarity. To understand scale, consider this. In every human body, there are roughly 7 octillion atoms. The vast majority of those hydrogen atoms, protons with their single electrons, formed in this epoch. Each one has traveled a lineage from the earliest plasma through nucleosynthesis, through recombination, and into stars, clouds, planets, and cells. In that sense, we carry within us the memory of first light. The universe, though still dark to the human eye, now contains visible light. Stars have not yet formed. There are no galaxies. But the stage is set. Gravity, working slowly and silently, begins to draw together the small fluctuations in matter left over from earlier epochs. These overdense regions will collapse into stars and galaxies over hundreds of millions of years. But the framework is already there. The light released during recombination travels still. It does not scatter or fade. It stretches, cools, and whispers its message through the void. We detect it with antennas, satellites, and instruments cooled to near absolute zero. And every time we look, it shows us the same picture. A universe, young and hot, just beginning to become complex. This light carries ancient secrets. Accidents reveal cosmic truths. In 1964, 2 radio engineers, Arno Penzias and Robert Wilson, were calibrating a large horn antenna in New Jersey. They weren't searching for the universe's origin. They were trying to eliminate background noise. But no matter how they tuned their equipment, no matter how thoroughly they cleaned their detector, even scraping away pigeon droppings, the noise remained, a persistent hiss, the same in every direction. Unbeknownst to them, they had stumbled upon a signal from the beginning of time. A glow predicted decades earlier by physicists like George Gamow, Ralph Alpha, and Robert Dick. This hiss was the red-shifted remnant of the first light released during recombination. The cosmic microwave background, or CMB. This light, now cooled to a nearly uniform temperature of 2.725 Kelvin, fills the universe. It's not visible to the eye, but its presence is undeniable. It is the oldest light we can observe, traveling for over 13.8 billion years, a direct messenger from the young cosmos, a faint glow whispering the past. At first glance, the CMB seems too smooth, an even wash of microwave radiation across the sky. But with precise instruments, we detect tiny variations in temperature, just 1 part in 100,000. These fluctuations are not noise. They are the imprints of early density differences, the seeds from which all cosmic structure grew. Where the radiation is slightly warmer, matter was slightly denser. These pockets eventually collapsed under gravity to form galaxies, clusters, and filaments. Over the decades, satellites like COBE, WMAP, and most precisely, Planck, have mapped these variations in detail. The Planck mission revealed not just the temperature of each spot, but the polarization and spatial distribution of the light. These data tell us about the shape of the universe, the amount of dark matter, the age of cosmic expansion, and the fine-tuning of fundamental constants. One striking feature of the CMB is the scale of its acoustic peaks, the baryon acoustic oscillations frozen into matter after recombination. Today, these sound wave echoes have grown into structures about 500 million light-years across, vast patterns of density that organize the modern cosmos. The CMB is not only a map of the past, it is the blueprint of everything that came after. And then, darkness. After the release of the CMB, the universe entered a time with no new light. There were no stars yet, no galaxies. The atoms formed during recombination drifted silently through space, slowly coalescing under gravity. This period, lasting from 380,000 years to around 100 million years after the Big Bang, is known as the Cosmic Dark Ages. During this era, the universe was filled with neutral hydrogen and helium. Light existed, but none was produced anew. The photons of the CMB continued on, redshifting into longer wavelengths, cooling as space expanded. But the cosmos itself remained unlit, awaiting the ignition of the first stars. It's a time we cannot yet see directly. The CMB shows us the edge of this darkness, the surface of last scattering. Modern telescopes can peer deep into the epoch of galaxies and reionization, but the dark ages themselves are hidden, traced only through indirect means, such as the 21-centimeter emission line of neutral hydrogen. Even this signal remains elusive. Still, this darkness is not empty. Within it, gravity works quietly, pulling together the tiny fluctuations in matter density. Dark matter, unseen yet abundant, plays a central role. It doesn't interact with light, but its gravitational influence shapes the flow of ordinary matter, guiding it into clumps. These clumps grow, forming halos that will later host the first stars and galaxies. And so, while the universe is dark, it is not idle. Structure is forming. The first cosmic webs begin to emerge. Regions of higher density collapse while voids expand. All of it driven by the faint fingerprints left in the CMB. This era also deepens our appreciation of what we do not yet understand. The CMB confirms that ordinary baryonic matter, the stuff of atoms, elements, and people, makes up only about 5% of the universe. The rest lies hidden. Around 27% is dark matter, detectable only by its pull. The remaining 68% is dark energy, a force that will later accelerate cosmic expansion. Unseen forces shape the silence. The invisible guides the visible. As we peer deeper into the cosmos, we discover that what we see, stars, planets, galaxies, gas clouds, represents only a sliver of reality. The rest, vast and silent, exerts its influence from the shadows. These unseen elements, dark matter and dark energy, compose 95% of the universe, shaping its past, its structure, and perhaps its fate. The first hint came in the 1930s when Fritz Zwicky, studying the Coma cluster, noticed that the galaxies were moving too fast. They should have drifted apart, unless held together by far more mass than he could see. Later, in the 1970s, Vera Rubin measured the rotation curves of spiral galaxies. She found that stars at the outer edges moved just as quickly as those near the center, defying the predictions of Newtonian gravity based on visible mass. The galaxies, it seemed, were surrounded by enormous halos of invisible matter. This substance, now known as dark matter, does not emit, absorb, or reflect light. It reveals itself only through gravity, It binds galaxies together. It sculpts the large-scale structure of the cosmos. Without it, the universe would look entirely different. Loose, scattered, fragile. With it, cosmic filaments stretch for billions of light years, connecting clusters like threads in a celestial tapestry. What is it? We don't yet know. Theories include WIMPs, weakly interacting massive particles, and axions, particles that barely touch ordinary matter. Others suggest MACOs, massive compact halo objects like rogue planets or black holes. Observations of massive structures like TON 618, one of the largest known black holes, hint at the gravitational muscle required to form such entities in a dark matter-rich cosmos. Still, direct detection remains elusive. Dark matter does not shine. It does not scatter. Yet without it, galaxies unravel. Galaxy clusters disband. Even the early universe's delicate pattern of structure, visible in the CMB, would vanish. Then there is the other mystery, dark energy. In 1998, astronomers observing distant type IR supernovae made a startling discovery. These exploding stars, used as standard candles to measure cosmic distance, were dimmer than expected. The universe, it turned out, wasn't just expanding, it was accelerating. This acceleration began roughly 5 billion years ago, reversing the gravitational slowdown of the earlier universe. The force responsible was dubbed dark energy, a pressure that acts not locally but on the fabric of space itself. Unlike dark matter, which pulls, dark energy pushes. It stretches space, driving galaxies apart ever faster. What is it? Again, we're not sure. Some models treat it as a cosmological constant, an unchanging energy of the vacuum. Others propose quintessence, a dynamic field that evolves over time. Both remain speculative, constrained by observation, but not yet explained by theory. And yet, the numbers are clear. Today, the universe is composed of about 68% dark energy, 27% dark matter, and only 5% normal matter, the atoms that make up everything we know. This imbalance forces a deeper reflection. Why do the constants of nature take the values they do? Why does the fine structure constant, 1/137, as noted by Richard Feynman, permit chemistry, stars, and life? Why does dark energy exist at all, and why is its strength just enough to accelerate the universe, but not enough to tear it apart? Shadows and pressures balancing our existence. These mysteries don't diminish our understanding, they deepen it. For all we've learned, from inflation to nucleosynthesis to recombination, the most fundamental questions remain open. Why does the universe exist in a form that allows complexity? How does the unseen determine the course of the visible? The cosmic microwave background marked the universe's first visible light. The Dark Ages, its first silence. The formation of stars, galaxies, and black holes brought new illumination. But behind it all, these invisible agents, dark matter and dark energy, have remained constant companions, sculpting and expanding the cosmos beyond our reach. As we look forward, we confront new uncertainties. Will dark energy continue its gentle push, leading to a cold, ever-expanding future? Will the acceleration increase, tearing apart galaxies, stars, even atoms, a scenario called the Big Rip? Or will dark energy fade, slow, or reverse? We do not yet know, but we continue to measure, observe, and imagine. The journey from the first fraction of a second to the present day reveals a universe filled with pattern and paradox. Simplicity gave way to complexity, symmetry broke, and from it came diversity. The laws of physics, balanced so precisely, permitted atoms, stars, planets, and thought. From a hot, formless beginning emerged a cosmos capable of questioning its own origin. And perhaps that is the most profound aspect of all, that the universe, through us, has become self-aware, not in entirety, but in parts, brief flashes of understanding scattered across time and space. The cosmos unfolds, and we listen.